Good morning, dear students. In the last class, we studied about liquid pressure, the laws of liquid pressure, and we also studied about hydraulic machines, which were based on the principle of Pascal's law, which is directly related to liquid pressure. Today's class, we are going to study about atmospheric pressure. We all know that the earth is surrounded by an envelope of air, and this envelope of air exerts a thrust on the earth's surface. Now, why does it exert a thrust on the earth's surface? Due to the weight of the air column acting downwards on the earth. And if we want to find out the atmospheric pressure due to the air column of air, it is given by the formula thrust exerted by the column of air upon the area on the earth's surface on which that thrust acts. So therefore, how can we define atmospheric pressure? We can define atmospheric pressure as the thrust exerted per unit area on the earth's surface due to the column of air. Now let us see how can we calculate this atmospheric pressure. We should know that the weight of the column of air which is acting per square centimeter area, that weight of the column of air is approximately equal to 1 kilogram force. Now, if 1 kilogram force is acting per square centimeter area, then the atmospheric pressure will be given by 1 kgf per square centimeter. Now let's do the conversion. Let's convert kgf to Newton and square centimeter to meters to square meter. We know that 1 kgf is approximately equal to 10 Newton, so I substituted 10, and 1 square centimeter is equal to 10 to the power minus 4 square meters. When I substitute the value and I bring this up, what do I get? Atmospheric pressure is equal to 10 multiplied by 10 to the power minus 4 power becomes plus 4, which is equal to 10 to the power 5 Newton per square meter. And this implies that a thrust of, what is 10 to the power 5? 1 lakh Newton. 1 lakh Newton acts on every square meter area of the earth's surface. Okay, now if we look at our human body, on an average, the surface area of human body is equal to 2 square meters. We know that the thrust per square meter is equal to 1 lakh Newton. So 1 lakh Newton. So it means that the thrust exerted on an area of 2 square meters would be equal to 2 lakh Newtons, which is approximately equal to the weight of 2 elephants. You will be surprised to know that on our body, a thrust equal to 2 lakh Newtons constantly acts due to the atmospheric pressure. But then the question arises that why are we not able to actually feel this enormous thrust on our body? So let us answer and let us see why can't we feel this enormous thrust? Actually, what happens, the blood which is flowing in our blood vessels, constantly flowing in our blood vessels, is flowing under pressure, and that constitutes the blood pressure of our body. Now, why are we not able to feel the atmospheric pressure? Because the blood pressure balances our atmospheric pressure, due to which we are not able to feel it. Now, let us look at a special case. When we go to higher altitudes, what happens? The height increases. Now, as the height increases, the density of the air reduces with height. Okay. Now, when the density of air will reduce, what will happen to the thrust? The thrust will be less. Why will the thrust exerted be less? Because the density of air is less. Okay. Now, when the thrust exerted will reduce, what will happen to the atmospheric pressure? It will also get reduced. So, therefore, the blood pressure will exceed the atmospheric pressure and when we go to higher altitudes. So due to which what happens is that we may face the following symptoms. That is, our nose might bleed, our ears will get blocked, we will have a headache or nausea, and we will feel uneasy. All these symptoms are faced by you when you move to higher altitudes. You must have experienced, students, that when you go to hill stations, when you travel from Chandigarh to a hill station which is at a higher altitude, you might face these problems. Sometimes you feel that you have nausea or a headache, or you feel uneasy, or your ears get blocked. The reason behind this is that the blood pressure exceeds the atmospheric pressure. And why does the blood pressure exceed the atmospheric pressure? Because the density of the air reduces with height, and therefore the atmospheric pressure reduces. So the blood pressure exceeds the atmospheric pressure and we feel all these symptoms. Okay. Now, here I have drawn an activity for you, and this activity will demonstrate to you that what is the effect of atmospheric pressure on us or on any object on the surface of the earth. This is called the collapsing tin experiment. Now here what have I done? I have taken an empty tin can and I have put a little water in it, and I keep this tin can to heat. Okay, now when the heating takes place, what happens? The water starts heating, and after some time it will start boiling and steam will rise up. Now as the steam rises up, what happens? The outer atmospheric pressure is acting on the tin can, and due to the steam there is a tremendous pressure inside the can. So the pressure inside due to the steam balances the outer atmospheric pressure, and due to which the tin can remains as it is. Now in the second case, what happens is I close the mouth of this tin can. Now when I close the mouth of the tin can, the steam is trapped inside. Okay, and I pour ice cold water on this can. On pouring ice cold water, what happens? The steam inside the can will condense and a low pressure will be created inside, but the outer air pressure is the same. Now in this case, what happens is that the air pressure exceeds the inner pressure. Pressure is less and the outer pressure is more, due to which you will see that the tin can will collapse or it will get smashed. So the condition is the air pressure increases the steam pressure, and here the air pressure is equal to the steam pressure. So children, you have seen that what can be the effect of outer atmospheric pressure on our bodies if the blood pressure is not there to balance it. Okay. Now, I will discuss some consequences of atmospheric pressure. These are some common consequences, and I'm trying to explain this to you with the help of diagrams so that you can understand it in a better way. Now, this is my first consequence which I'm picking up. This is how are we able to suck a drink with the help of a straw. You all know that when you want to drink a cold drink or maybe lime juice, you use a straw to drink to have your drink. Now how does it work? Actually what happens is when you put the straw inside the drink, the straw contains some air. Now when you try to suck the drink through the straw, first of all the air from the straw is sucked up and it moves into the lungs, due to which a low pressure is created inside the straw, and outside what happens is atmospheric pressure is acting on the drink. So what happens? The drink moves from high pressure to low pressure, and therefore it can move into the straw, and thus we are able to conveniently drink it through the straw. So that is how the drink moves from high pressure, that is from the glass, to low pressure, that is inside the straw, into our mouth. Now let us look at the second example here. This is filling up of a syringe with a liquid. Now here I have drawn a syringe which looks like, this syringe has a barrel and it has a plunger. Now initially this syringe is dipped into a vessel containing a liquid. Now what do I do here is I pull up the plunger. Now when I pull up the plunger, what happens is that a low pressure is created inside the barrel, and you can see that the atmospheric pressure is acting on this particular liquid. So the same thing happens over here is that the liquid rises from high pressure to low pressure. Where is the high pressure? Outside. And where is the low pressure? Inside the barrel. So therefore this particular syringe gets filled with the liquid. So you can see that the conditions remain the same. That is, the liquid moves from high pressure to low pressure. Now let us look at the third example. Now in the third example, I have taken filling of ink in a fountain pen. Now children, what do we do in order to fill a fountain pen? We dip the nib of the pen inside the ink bottle. Now as I dip the nib of the pen inside the ink bottle, the rubber tube of the fountain pen is pressed. As soon as the rubber tube is pressed, what happens? The air is pushed out of the rubber tube. So a low pressure is created inside the fountain pen, and the ink, the atmospheric pressure acts on the ink. So there is high pressure outside. So thus the ink can easily move from high pressure to low pressure. That is from the bottle inside the fountain pen. And this is how ink gets filled in a fountain pen. Now let us look at the fourth example. This is, I have shown a rubber sucker over here, which is to be fixed onto a glass surface. Why glass surface? Because it's a smooth surface. And this rubber sucker can easily get stuck on it. Now how does it work? First of all, when we take the rubber sucker and hit it against the surface, air is forced out of the rubber sucker, creating a partial vacuum. Now, inside there is a partial vacuum created, that is a low pressure, and from outside, atmospheric pressure is acting on this rubber sucker. So what happens is, there is high pressure outside, there is almost partial vacuum inside, due to which the rubber sucker gets easily stuck on the surface and cannot be removed. So this is how the rubber sucker functions. Now let us look at the fifth example. This is action of a siphon system. Now what is a siphon system? It is a system here which has two tanks. I have named it as P and Q. Now there is a pipe over here connecting vessel P with Q, and I want to actually force out the liquid from P to Q. What will it easily rise up? No, it is very difficult for the liquid to rise against gravity. Now how does it work? I have prepared a stepwise sequence for you. First of all, what is going to happen is that the air from the lower section of the pipe has to be sucked out or has to be removed, creating a partial vacuum or low pressure here. Okay, now as the air moves out, a low pressure is created inside the pipe. And as the low pressure is created, you can see that the atmospheric pressure is acting from outside. Now the atmospheric pressure acting from outside pushes the liquid inside the pipe easily, and thus the liquid rises up in the pipe, and then later on what happens? The liquid moves from P to Q easily because the force of gravity pulls it downwards. So this is how the siphon system works. Now the last example is taking out oil from a sealed oil can. Here I have shown two cases. In the first case, you can see that there is a sealed oil can, and this sealed oil can has only one hole. Now inside a sealed oil can, there is a little gap which has air, and you can see that the pressure is exerted by the oil on its by the oil column onto this hole, but the pressure is very less. The pressure due to the oil column is very less as compared to the atmospheric pressure which is acting from outside, due to which the oil is unable to come out or flow out from the single hole. Now how can the oil be taken out? Then what will I do is, I will make, it is sealed, okay, so I'll make another hole on the top of the can. Now this will help the oil to come out. Now what's the reason behind it? Now when I make a hole opposite to the on the sealed can, what happens is the atmospheric pressure acts on the oil inside. So now this time what happens? The atmospheric pressure plus the pressure of the liquid column adds up, and that increases and the outer atmospheric pressure is less. So due to that, what happens is that the oil easily flows out from the can. So you saw, children, that from all these examples which I discussed with you, I proved that how liquids move from high pressure to low pressure, and how is atmospheric pressure exerted on our bodies and on different objects on the surface of the earth. Thank you.